Hello, welcome to my talk. My name is Lasse Klingbeil. I'm from the Institute of Geodesy and Geoinformation from the University of Bonn, and I will tell you about how to accurately georeference sensor data from mobile platforms in agricultural applications. So I will answer the question, where exactly is my plant, especially in the field. So that could mean I want to know where this plant here is. I want to assign a coordinate to it, as it is shown here, a coordinate which is globally valid and not in some local coordinate system. It doesn't necessarily mean that I want to know the coordinate of the plant. It can be also the coordinate of an organ, of a leaf or something else. So why would I want to do that? In precision agriculture, there are three main things that we have to do. The first thing is building a map. So assess the current status of the crop, of the field, where are about the status of the soil or the plant height or anything like that. So I need to assess the current status of the field. And next task is monitoring. So I understand what's happening in the field. I observe changes over time. I potentially apply some models. I also could predict changes. And then in the third part, I want to act. So I want to do the right thing at the right time, at the right place. And these are the three things which all involve that I know where the things are going on. So what's happening here, and where I have to do some specific thing like fertilizing or spraying herbicides. Interestingly, in engineering geodesy, so that's a discipline where I come from, there's a strong link to these tasks in precision agriculture. So the main tasks in engineering geodesy are surveying, like building a map, assessing the state. Monitoring means detecting changes over time, modeling them, predicting things, so see what's going on over time. And the last one, it's called stakeout. It means go to a specific position and do something. So there is a strong link between those, and this is why I'm telling you these things. Recently, there has been a trend in doing all these tasks, these engineering geodesy tasks, from mobile platforms. That means I do the measurements during motion. On a platform, you see many examples here, like cars, planes, helicopters, even satellites. They move, and while they move, they do their measurements. And I want to tell you a bit what the challenges are in doing that, what are the necessary steps, and what you can do if you do that in agriculture. So what platforms and sensors do we have in agriculture? So there are a few of them, so from different scales. So the main thing is to look at different scales. So you have satellites with like a 10-meter resolution on the ground. You have planes, they are in the order of 1 meters. Drones can go down to 1 centimeter or even millimeters. And then you have ground vehicles which can give you like precision millimeter resolution on the ground. And with these different resolutions, you can also see different things, right? With the satellites, you look more for regions. You can go down to fields, stands, single plots like you would need in breeding applications, single plants, or even organs like the wheat ears that you can see here. So we will focus in this area. So what you need to do if you want to have this with a particular centimeter accuracy in a global coordinate system. So how do we usually do that? So you have a platform, as I mentioned before, and with this platform I drive or fly over the field, right? So we have a drone with some sensor, we have some plants, and we have some vehicle driving in this field. And the goal is to create a map and to know where exactly that plant is on that map. And this is a goal, and there are different steps you need to perform in order to do that. So one is to look at the sensor observation. So to answer the question, where is my plant in the sensor data? So if you look at different sensor data, we have examples like a camera, which is a two-dimensional sensor, right? It gives you a pixel coordinate or something. Then we have a 3D scanner, for example. Then the actual observation is some point given in the sensor coordinate system. And you could also have a line scanner, for example, as it is sometimes on helicopters or planes, or also on ground vehicles, where you just get an angle and a distance for each measurement. So this is how the sensor observations look like. And what we also need is, we need to know where the platform in the world is. So where is my vehicle in the world? So that means I need to know the orientation and position of that vehicle. So this is usually done if you want to have global coordinates, you have to use GNSS. And you don't have to use, you cannot only use a normal GNSS like we use from our smartphones, we know from our smartphones or our navigation systems in the car, we need real-time kinematic GNSS. So this real-time kinematic GNSS provides with 10 Hertz roughly centimeter accuracy in the field, in real time or in post-processing, depending on what system you use. It depends on the fact that you have reference data available, which means that I have my satellite here, my receiver here, I get my satellite observations, and I have another antenna somewhere on a fixed position where I observe the same satellite observations, and then I can do some different thing and remove a lot of errors. So this is what I need to do to go down to the centimeters. So that's what is actually pretty standard already today in agriculture. So a lot of machinery already has RTK GNSS to do row following, not row following, to do parallel driving, automatic parallel driving systems and so on. But GNSS is not enough. So it's not enough to have the position of the vehicle. You need a 3D orientation as well. Yeah, so you need 3 angles in order to know, for example, where your sensor is actually pointing and where your sensor is looking at. So this can have a big influence on your accuracy. Luckily, there are systems which provide a 6-dimensional, 6 degree of freedom pose, like position and orientation, and these systems are available on the market, and you can use them. They're basically based on IMUs and GNSS, and they use Kalman filters and other algorithms to generate a trajectory. Like so here we see a trajectory, like a position of a vehicle driving around, and you see also that there is a changing orientation which is estimated similarly. So once we have this trajectory, we have the sensor observations, but then we need to know something else. We need to know, where is my sensor on the vehicle, right? So we need the relation between the sensor and the vehicle is also a 6 degree of freedom transformation. It's a rotation and translation. We need to know it. There are ways of doing this. It's called system calibration. I will not go into details of that. So if we summarize this, we end up with this equation here. It's a georeferencing equation where we have the measurement of the sensor and the sensor system, then we have some transformation from the sensor to the vehicle system, then we have another transformation from the vehicle to the global system, which then at the end gives us the point that we measured here in some global coordinate system, such as this map, right? And one question is, what accuracies do we need on the way from here to here for the different aspects to get a centimeter accuracy here? So let's have a look. First thing is, if we have a position uncertainty, which is somewhere here in the system calibration or in the vehicle trajectory estimation, then this directly translates to a position error in the result. That's pretty simple. If we have an orientation error, it becomes more complicated. So if we have an orientation error here, then this translates to a position error in the result, which depends on the distance between the sensor and the object, right? So if we look at numbers now, if we have a centimeter accuracy somewhere here, this translates directly to a centimeter accuracy here. If we have a 0.1 degree orientation uncertainty here, then depending on the distance, this can go to millimeter or centimeter position errors, depending on 2 differences that are put here as an example. There's another thing which is important in these types of systems, it's time. So if this assumes here that I know for the time that I do my measurement, I know the trajectory. And if there's an error in that, like that I have a 1 millisecond another time where I put my sensor measurement when I took my sensor measurements with respect to where I have my trajectory estimation, then this also translates to an error, right? So if I move, and this depends on the moving speed of my vehicle. So if, for example, I move with 30 kilometers per hour and I have a millisecond error, then this translates to a centimeter error in the trajectory and again in the result. If I have a 100 degree per second rotational velocity, then this translates to 0.1 degrees in orientation and again to the numbers I've shown before. So a millisecond is already not so easy to achieve. So you have to do things to make sure that this millisecond is actually there. So finally we can say do not exceed the above values if you want to have centimeter accuracy here. So anything which is more than these numbers that I've shown here brings you serious trouble in achieving centimeter accuracy on that side. So let's go to some examples that we've done in the last years where we used these methods in order to show some of these tasks that I have here. So let's start with building a map. Building a map, we have a in-house developed sensor system which we put in this example on a bus, which has a high accuracy laser scanner, RTK GNSS and some very high grade IMU. And with this we did some system calibration which was very accurate, so it was in the order of centimeters and 0.01 degrees, so below the things that below the requirements as I said before. And with this we can generate georeferenced point cloud like this one. So this is here measured with this particular system. The accuracy in total was evaluated using points. Yeah? So we put some points in the environment where we knew the exact coordinates, then we extracted the scanned points from the scan, and then we looked on the accuracy. And it was all below a centimeter. So that's a pretty good result. So can we use that in agriculture? Currently we're working on a system where we use a similar principle in the field, where we drive over the field with some scanner pointing down to generate a point cloud. And this is just a preliminary result, but we have this robot here and we have this scanner and we can already generate georeferenced point clouds like this one. The scanner is not as good here, so it's pretty noisy, but this may change in the future. Let's go to another example, which is a monitoring part. So we want to observe something over time. And this is, in this example, done via UAVs. With a UAV, you can fly over the field and you use structure from motion techniques in order to generate a 3D point cloud of that field, which is georeferenced. There are different ways of georeferencing. I want to go into detail here. I just want to mention that we can generate the position of the actual camera in the air, which is similar to what I've shown before, but also we can use ground control points which we have to put on the ground and measure. This is also used, and also combinations of this are used. In this case we used a combination and to generate plant height models. Yeah. So here we flew over the same area different times, and then we subtract the different point clouds from each other in order to get a crop height. And what we need to have a georeferenced point cloud, otherwise subtraction doesn't work, of course. So here we make use of the fact that we have a centimeter accuracy in the georeferencing, and then we can generate growth rates of different genotypes of winter wheat, for example. The last example is something which is acting, means doing the right thing at the right time at the right place. And the example here is a coordinate controlled seeding of sugar beet. So the goal here was to generate a grid of sugar beets, which can be where we can go with a mechanical hoe from both sides, right? So we have a perfect rectangular grid of sugar beets. And the idea was to place the sugar beets really controlled by the GNSS coordinates. Again, we have GNSS, RTK GNSS. We have a real-time processing using Kalman filtering, and we use different other sensors to generate, in this case, a 2D position and one angle, and then to control this seeding wheel here so that it drops the seed at the right position. The result can be seen here. This is the track of the 4 seeding units, and this was used to actually put the seeds out. And then after the plants emerge, these 2 guys here measure them, each of them with a geodetic instrument, and this is a deviation from the position where it was meant to be placed. So we can say that the plants was emerged about 2 centimeters away from where they're supposed to be. So this was done already a few years ago, but this is showing how you actually do something at the right position. To sum it up, so what do you need for centimeter accurate plant coordinates? You need high precision GNSS in the order of centimeters. You need a precise orientation determination in the order of 0.1 degrees. And you need a very good synchronization of the sensors, which is in the order of milliseconds. And what you also need is some system calibration, which is very accurate. There are other potential future improvements that I haven't talked about today, which is like SLAM type methods, using the scans and the images of the data and some global optimization procedures, which may improve the result, because then the orientation measurement is not needed as accurate anymore. This then, if you have all these things, you do generate centimeter positions. This is just showing a vision, right? It's a tomato plant in lab conditions, but the goal is to generate these in the field using a robot. So this would be a vision, which is I know it's a bit challenging, but I'm pretty optimistic that we come to that point at some point. With this, I want to thank you.